Welcome to the Heap Feng Shui talk. This is the future of exploitation, so I hope you won't be disappointed. So what is Heap Feng Shui? Besides just being a cool title for a presentation, it is also the art of arranging heap blocks to make exploitation easier, to ensure that when you overwrite data on the heap, you're overwriting the exact block that the exploit author intended. It is not a new technique, but the implementation that I'm going to present makes it very, very easy to implement things like this in Internet Explorer. I'm going to talk about these heap manipulation techniques implemented in JavaScript, which makes it very easy to exploit a variety of browsers. The actual implementation that I'm going to demonstrate, and it should also be on the CD, is supports Internet Explorer 6, I think 5, 6, and 7. But certainly these techniques can be applied to pretty much any system that supports JavaScript or a similar execution environment. In fact, we have seen some more sophisticated exploits that are using similar techniques even without any client-side scripting. So I will talk about those briefly in a little bit. So this talk is going to have a couple of parts. First, we're going to start with, is this echo normal? Or? Okay. So first we'll start with what the state of the art in browser exploitation is. I will cover a couple of exploits that have come out over the last year and the techniques that they used. I will talk about the traditional stack and heap exploitation methods and why they no longer work or work in very limited circumstances. Then I will talk about, I will present the heap manipulation. Higher? Is this better now? Okay. So we'll start with the state of the art. Then I will introduce the heap feng shui idea, which allows for these precise manipulation of the heap. And I will show how to implement it using Internet Explorer. In order to do this, I'll have to cover the Internet Explorer heap internals. I'll show how the different pieces and components of Internet Explorer allocate memory and how we can utilize these components to get our blocks to be in the right places. Then I will demonstrate the so-called heaplib JavaScript library, which is a very user-friendly, object-oriented JavaScript library that you can import into your exploit, and it provides you with a variety of functions that are very useful for heap exploitation. The source code of the library should also be on the CD. It is BSD licensed, so you can use it pretty much any way you want. Finally, I will talk about, I will give specific examples of the heap manipulations that are possible using this library. I will show one of the exploits that I developed using the library. I will walk through it and demonstrate how it works. And then I will talk briefly about the potential mitigations for preventing techniques like this from working in the future. None of the mitigations are very good, though, so if somebody wants to work on a cool project, maybe they can figure out a better way to stop this. I personally prefer working more on the attack side than the defense side. So let's start with the browser exploits that we've seen recently. The generic exploitation techniques that have served us very well for a number of years no longer work very well, or work in very limited circumstances. Probably the most common and standard exploitation technique is the buffer overflow on the stack, where you override the return address. and redirect the program execution to your shell code. This is pretty much mitigated by the GS flag in the Visual C++ compiler. In almost all cases, it prevents the exploitation of return address overrides. There are some exceptions to that. There have been cases where a function was not protected by GS, even though it should have been. The ANI exploit in the beginning of this year was one of those examples, but this is a pretty rare occurrence. So you can pretty much count that your standard vanilla buffer overflow on the stack can no longer be exploited just by overriding the return address directly. The other thing that you can override on the stack are the SEH frames. By overriding these and causing an unhandled exception, you can get shellcode execution because your shellcode will appear to be registered as an exception handler. The SEH frames are also stored on the stack. They're right before the return address. So they're pretty convenient. They're a pretty convenient exploitation method, but they also don't work very well in 2007, mostly because of the safe SEH feature in the recent versions of Windows. If your code was compiled with the safe SEH flag, all the exception handlers in the program will be registered in a special table inside the binary. And if you try to execute an exception handler that is not in that table, the operating system will just refuse to jump there. And obviously, your shell code will not be registered as a valid exception handler. And since this exception handler table is in the actual binary and it's in a non-writable segment, you can't really do much with it. So if your binary is compiled with this option, then SEH overrides are also, in almost all cases, not exploitable. Finally, the last thing you can do with a stack-based buffer overflow is you cannot override the return address because of the GS protection. You cannot override the SEH frame because of the safe SEH. What you can override are the local variables that are stored on the stack frame before the SEH frame and the return address. Overriding those also no longer works because the latest versions of Visual C++ reorders the local variables so that your stack buffer, where your buffer overflow most likely is located, will be at the end of the stack frame. So there will be no pointers or any other important pieces of data after it. So you will not be able to override them. In addition to that, the compiler will move the arguments of the function, which could also be pointers. It will move them to the top of the frame. So you can no longer override those either. So pretty much this makes the standard case of buffer overflows on the stack non-exploitable. So what does this leave us with? Heap overflows. Unfortunately, the generic heap exploitation methods for heap overflows have also been getting harder and harder to implement. Probably the most standard method is using the doubly linked list of free chunks, which is a list that links all the free chunks on the heap. In the past, you could use the unlink operation from this doubly linked list to override an arbitrary 4-byte location in the program. Unfortunately, in XP Service Pack 2, in 2003 in Vista, you can no longer do this because the heap allocator verifies the integrity of the doubly linked list. This was a very cool exploitation technique because it was completely generic. It didn't matter what application you were in, as long as it used the standard Windows allocator. You could just override the doubly linked list and it would work. Unfortunately, you can no longer do that. On top of that, in XP Service Pack 2, there is an 8-bit cookie in the header of each chunk. And before most operations performed by the heap allocator, the cookie will be checked. And if it doesn't contain the correct value, the heap allocator will bail out. So this means that you're no longer able to overwrite override the header. And on Vista, this has been improved by actually XORing the entire header, which serves to completely make it impossible to override the header with data that will appear valid because you do not know what the XOR key is. And finally, one of the attacks, I believe Matt Conover first found this, if I'm not mistaken. The look-aside linked list, which was a single linked list data structure used by the heap allocator, could be used to do a 4-byte, no, not a 4-byte, all right. It could be used to do heap exploitation in a mostly generic way as well. But in Vista, the look-aside has been removed completely and is now replaced by the low fragmentation heap, which is much more secure and doesn't have data structures like that. So what this means for us is that we cannot exploit generic heap overflows by attacking the heap allocator, because the heap allocator has been hardened to a level where, in the generic case, there is nothing that you can do with it. So what's left? I mean, does this mean that there are going to be no exploits for Vista, for example? Well, obviously not, since we've seen some already. The ANI exploit, which was one of the first vulnerabilities in Vista, was a very interesting case because it was in a function that was not protected by GS, and it still contained a stack overflow. The compiler doesn't insert the GS protection for all functions because of the performance impact. It uses a heuristic to detect which functions have buffers that are likely to be overwritten. Unfortunately for Microsoft, in the ANI case, the data structure that was being overwritten on the stack was not an array, so the compiler heuristic did not insert the GS protection. And you could exploit the stack overflow like it was back in 1999. There was no protection to bypass it all. Unfortunately, this is a very rare case, and I doubt that we will see a large number of these vulnerabilities. The other avenue that's still open for attack is the use of uninitialized variables. And by uninitialized variables here, I mean not only variables that have never been written to, but also variables that might have been initialized, but the data there becomes invalid and is used afterwards. For example, a use after free vulnerability I would consider an uninitialized variable bug, because you have a free block that some you have a block on the heap that some pointer points to, and after this block is freed, the pointer becomes invalid. But if the program still uses it, it will access the data that was just freed. And in the meantime, this data could have been overwritten, it could have some different contents, it could actually be completely unmapped, so maybe it's not even valid memory. Halvar Flake did some pretty cool work on exploiting uninitialized stack variables. His work was mostly focused on how to use static analysis to figure out which functions had overlapping stack frames. So you could use different code paths to initialize the uninitialized data, and then use another function, and then call another function that used this data, and now you control the values in it. Unfortunately, a lot of these uninitialized variables are pretty hard to exploit if you don't have good control over the contents of the heap. For example, in the use after free case, you need to be able to take the block that had just been freed and allocate it, fill it with your own custom data, perhaps free it again. So the heap manipulations that are required there are more complicated, and this is what prompted this research. The final thing that you can attack is the application data on the heap. Since you can no longer use the heap headers, you can use the data that's after them, which would be specific to the particular application and the particular code that uses it. Maybe you have an application-specific memory allocator that still uses a doubly linked list that's not protected by the safe unlinking feature. Maybe you have function pointers somewhere on the heap that you can override. Maybe you have C++ object pointers. The difficulty there is that because the heap is so dynamic, you don't really know what data is located after the buffer that you're overriding. But with heap feng shui, you can make sure that the data located there is the data you want. So you'll find out how in a little bit. Let's look at one of the exploits that came out last year. It's the WebView set slice exploit. And it was added to the Metasploit framework, and it worked pretty well in most cases, except that it relied mostly on random luck. So in some cases it would work, in others it won't. The set slice exploit was a buffer overflow where the buffer was underflown, so the data before your buffer was overwritten. What the Metasploit exploit did was fill a large chunk of the heap with shellcode. This is called heap spraying. And then trigger the vulnerability repeatedly in a loop, overriding random pieces of data on the heap with pretty much random pointers. And hopefully, if you're lucky, one of these pointers, the data that you overrode would be a function pointer on an object pointer, and calling that function pointer would get shellcode execution through all the shellcode that you've placed on the heap. In most cases, it actually worked. I was very surprised. It did work pretty well, but it was not 100% reliable. So I was trying to improve upon this exploit. But before we get to that, let's talk about heap spraying for a little bit. So you're probably mostly familiar with heap spraying, but here's a very quick overview. It's been used in almost all exploits, Internet Explorer and other browser exploits since 2004. It relies on the fact that JavaScript strings are actually stored in the normal heap area, and they're not really modified in any way. So you can build a string that contains the bytes of your shellcode preceded by a long knob sled, and you can fill the heap with this string. It's not always necessary to fill the entire heap. You can only do 200 megs like the code that's shown there. Here's how this looks in the actual memory address space. So this would be the heap of Internet Explorer. We have a few allocated blocks shown in blue down on the bottom. There is some fragmentation, so there are some blocks that have been freed, so we have some free holes there. And then after that, we have a lot of empty space that hasn't been used yet. After we do the heap spraying, and after we allocate 200 megabytes of these strings that contain the shellcode, we're going to have the green area there filled with our shellcode. And it'll fill out all the holes caused by the fragmentation, and then it will fill out the rest of the memory. So if you have a memory layout like this, then jumping to an address that's somewhere inside the green area will get you shellcode execution, because the green area contains a lot of copies of the shellcode, one after another. One address that's commonly used is the 0C0C0C0C address, and I'll go into that in a little bit. I'll explain why this particular value has some interesting properties for us. But what you need to take from this slide is that jumping anywhere inside the green area will lead to shellcode execution. So if you can override a function pointer after you have done your heap spraying, and the program calls that function pointer, the function pointer will contain that address that you put there, 0C0C0C, which is inside the green area. And then the program will jump there, and it will land on your knob slide. It will execute it, and then it will reach the shellcode. So you're done. A more interesting exploitation technique is using this to exploit object pointer overrides. Now, object pointers in programs compiled with Visual C++ point to the object data, and the first 4 bytes of this object data contain a pointer to a vtable. The vtable contains function pointers for all virtual functions for this class, for the C++ class. So if we overwrite, so to exploit this, we need to spray the heap with 200 megabytes of shellcode. But as an upslide, instead of the standard OX90 byte, we will use byte C, which is a valid x86 instruction. It's, for all practical purposes, equivalent to NOP. We don't care about its effects. And it is also a 1-byte instruction, so it works well as an upslide. We will override, so we will fill the heap with this OC NOP-slide followed by shellcode, and then we'll override a function pointer with the OC value. Then we will wait for the program to call a virtual function of this object. When this happens, the program will treat the data located at address OC as a turn this off. It will treat the data located there as a fake object data. The first 4 bytes of this fake object will be the vtable pointer. But because we've filled the heap with this OC byte, the vtable pointer will also point to the same address, 0C0C0C0C. So now the program will use the same data, but it will use it as a vtable. Let's say that we're calling virtual function at offset 4. The program will read that data there, and that data is, again, 0C0C0C0C, because this is the byte that we filled the heap with. The program will use this as a virtual function address, and it will jump to our code located at 0C0C0C. Again, the bytes there are 0C0C0C, but this byte is also an executable x86 instruction that we're using as an upslide. So the program will execute these bytes and eventually reach the shellcode. Again, this is the standard technique used in a lot of exploits since 2004, but we will see how we can improve upon this. The problem with the set slice exploit is that it is HD, but it is often unreliable. If you're lucky, it'll work. So if you're going for mass exploitation, maybe it's good enough. You'll still get 50% of your targets. But if you're trying to do more directed, targeted attacks and you need high reliability, you need something better. The problem is that when you overwrite application data, you need to know exactly what the heap layout is. For example, for the set slice exploit, we were overwriting the block located right before us. If we could be certain that this block contained function pointers and object pointers, then we would have guaranteed 100% reliable exploitation. So what we need is to control the heap state of the application. And this is what I call heap feng shui. The heap allocator behaves deterministically. It's a very important property for our purposes. It means that if you do the same sequence of allocations, you'll always get the same result. Also, the blocks are mostly allocated in sequence. So if you start with an empty heap and allocate 2 blocks, which are shown there in blue, these 2 blocks will be located right next to each other. The first one will be in the beginning of the heap, the second will be after this. So we can use specific sequences of allocations to force the heap to have a specific layout. For example, if we start with a heap that looks like this, like the slide there, and we allocate 2 4-kilobyte blocks, they will be allocated, again, right next to each other. They're shown in orange on the slide. Then we will free the first block. We will free the first piece of data. So now we'll have this free block, but it will still contain the data that we put there originally because it hasn't been reused. Now, let's say that we trigger some kind of, we use an ActiveX object or just some other component of Internet Explorer that allocates a 4-kilobyte block. The heap allocator, in this case, will get the block from the free list, but the only thing on the free list is the block that we just freed, which means that the application will receive the same block that we freed that has been filled with the data that we put there. If that component, if that code has an uninitialized data bug, which means that it uses the data there without actually writing to it first, it will use the data that we put there, the values that we put there. So if we can use this to control a function pointer or an object pointer, we can apply the techniques that I described in the previous couple of slides and get shellcode execution. So this is the crux of the heap feng shui technique. Like, this is the most important piece of the presentation. Everything else is just implementation, technical details. But this demonstration here shows that if you do the allocations in the right order, and if you know what kind of allocations the application will do, you can influence where the application data will be located on the heap. So if we do this and the application is vulnerable, we just exploited an initialized data bug. So we want to do this in Internet Explorer, and we're going to use JavaScript to do it. Heap spraying already proves that JavaScript strings go on the standard Windows heap without being modified in any way. So it proves that we can allocate data on the heap that a lot of other pieces of Internet Explorer use. We also know that we control the data inside these blocks because that data is the strings that we put there. Now, if we have a way to allocate these blocks of a specific size, let's say you want to allocate a 256-byte block. If we have a way to do this, and if we have a way to free specific blocks, then we would be able to use the heap feng shui technique to control the heap state. But to do this, we need to look at how Internet Explorer actually uses the heap. So in this part, we're going to talk about the internals of Internet Explorer. There are three main components of Internet Explorer that are relevant to our exploitation efforts. Those are the JavaScript runtime engine, which most of its code is located in jscript.dll. The MS-HTML rendering engine, which is responsible for rendering HTML. It's located in MS-HTML.dll. And ActiveX objects, which are located in whatever DLL you're using, depending on the specific ActiveX object. I've put ActiveX objects here because a lot of the vulnerabilities over the past 2 years, which prompted the development of these techniques, were actually vulnerabilities in ActiveX objects. With Internet Explorer 7 and the ActiveX hardening, we're probably going to see less of this, but the techniques are still applicable to vulnerabilities in MS-HTML and other Internet Explorer components. So Windows processes usually have, they have at least one heap, which is called the default process heap, and it's created during the process initialization. But they can also create special dedicated heaps. So different components do have the capability to use different heaps. If we look at what kind of heaps the different Internet Explorer pieces use, we'll see that most of them actually use the default process heap because using a special heap requires more work. So it's easier for the programmer to just call heap alloc and not pass a special heap. So MS-HTML uses the default process heap. The JavaScript engine uses a special heap for its objects. So if you create an array object or some other kind of object, it will go on this special heap. But the strings that you create go on the default process heap. And this is very good for us because we want to use the strings because they give us the capability to control the data inside the allocated blocks. The ActiveX objects, most of them use the default process heap. There are some that would use dedicated heaps, but in the exploits that I've had to develop, the default process heap was the only one that I really had to be concerned with. So let's look at how JavaScript treats strings and how it stores them in the memory. The strings are stored as BSDR structures. It's an OLE type. You have the string data, which is in Unicode, so each character takes 2 bytes. The string data is preceded by 4 bytes of string size, and after that you have a 2-byte null terminator. So if you have the string AAAA, it'll take a total of 8, 10, 14 bytes. 4 bytes for the size, 8 bytes for the string data, and 2 bytes for the null terminator. So we can use the 2 formulas that are shown up there on the slide to calculate how many bytes would be required to store a string of a specific length. We can also go the other way and calculate if we want to allocate a block of a specific size in bytes, how long does the string need to be that we're going to create. So, for example, this here shows that if you need a 14-byte block to be allocated on the heap, you have to use a 4-character string. Now, one little catch is that all the sizes are actually rounded up to 16. So it'll be a 16-byte block instead of 14. So string allocation in JavaScript is not very hard. Now, the obvious way you're going to do it, which is with a string literal, shown there on the first line, is not going to work because the string literals are pre-allocated when the JavaScript code is parsed. But if you create a string dynamically during the execution of the JavaScript, which can be done using the substring function or by concatenating 2 other strings, the JavaScript interpreter will allocate a new block of the size that you requested, and it will fill it with the data that you want. So these two methods there give us the ability to allocate blocks of an arbitrary size with arbitrary contents, and that is very powerful. The second half of the puzzle is how to do free operations. Now, JavaScript is garbage collected. There is no way to explicitly free a piece of data. There is no free function that you can call in your string. It uses a mark and sweep. The Microsoft JavaScript interpreter uses a mark and sweep algorithm for garbage collection, which means that it walks through all the objects that have been allocated, and it checks which ones of them are no longer referenced, and then it frees all of those. It's triggered by a number of different heuristics, one of which is if you've allocated, I believe if you allocated 1,000 new objects, that will trigger the garbage collector to run. There are other ones. I think they're being continuously tweaked. But what we're going to use is the undocumented collect garbage function, which you can call directly from JavaScript, and it just executes the garbage collector. So we don't have to rely on any heuristics to trigger the garbage collector. It's a really neat function, and I'm glad that they put it there. So here's a little example of how we're actually going to allocate in free blocks on the heap. We have 2 functions there, alloc, which takes the size of the block in bytes, the block that we want to allocate. And then we have a free function. Now, the alloc function will take the size in bytes. It will calculate how many characters we need in our strings, which is bytes minus 6 divided by 2. And then it will use the substring method to chop off a piece of the padding string. The padding string is just a very long string that it has to be as long as the largest allocation that you're ever going to do in your JavaScript code. So we're going to use the substring method to just take this many characters, and this will allocate a block of that size in bytes. And on the bottom there, on the next to last line, we're going to call the alloc function to allocate 64K of memory. Then we're going to call the free function to free that string. The free function will set the str variable to null, which deletes the only active reference in the JavaScript code to that string object. And then we will call the garbage collector. The garbage collector will notice that there are no references to the string, and it will pass the string to the free function. So with this code, we have the ability to allocate strings of arbitrary sizes, arbitrary data, and free them arbitrarily. Unfortunately, when I first implemented this, it turned out that it didn't work very well. It didn't work always. Sometimes I was getting very weird results. So I had to go and reverse some code, and what I found out is that the strings were not actually allocated directly from the system memory allocator, but they were allocated through OLI Auth32 DLL, which implemented a custom caching scheme on top of the standard memory allocator. The point of the caching system was to have blocks that have been freed, to store them without actually releasing them to the system. And the next allocation that happens after that will get one of the cached blocks instead of going all the way down to the system memory allocator. It is not very clear why it's there, because I think that the system memory allocator with its look-asides and especially the low fragmentation heap in the most recent versions is probably much, much better than this caching scheme, but it's probably just a piece of old code that was left from a long time ago. So this caching allocator uses 4 bins for blocks of different sizes. So for example, blocks between 0 and 32 bytes go into the first bin, blocks between 32 and 64 into the second bin, and so on. So we have like 4 categories of blocks. Then I think blocks larger than I think 32K just get freed directly, so there's no caching for them. And each bin contains up to, it's an array that contains up to 6 free blocks. So if your cache for a certain size is full, then you can no longer, and then you free a block of that size, it's not going to go into the cache. It will just go directly to the system allocator and will get freed. Here's how the alloc and the free functions actually work. And what we want to do is, like, the reason we're looking at this memory allocator is because we want to ensure that all of our allocations come from the system memory allocator instead of the cache. And we also want to make sure that when we free a block, it goes directly to the system heap instead of getting stored into the cache. So to do this, we need to understand how the alloc and the free functions work. And you can look at the paper that accompanies the presentation, and I have way more detail about how the allocator actually works, but here's a very short overview. When we allocate a block using this allocator, first we find the right bin for this block based on its size. If that bin is empty, which means that there's no cache blocks of this size, then we just allocate a new block from the system allocator. If the bin is not empty and contains some blocks, we find the smallest block that can satisfy that allocation request, and then we return that block. If there are no blocks that are large enough there, we also go to the system allocator. It's a pretty simple algorithm, and the algorithm used by the free function is also pretty straightforward. If the bin for our size is not full, we're just going to add the block to it. If it is full, we're going to find the smallest block, the smallest cache block, and if it's smaller than our current block that we're freeing, we're going to replace it. So what the allocator is trying to do there is keep the 6 largest blocks that have been freed inside the cache. So it's trying to maximize the amount of memory that is being cached. So from the free function, one interesting thing to note is that if you free like a large block when it's getting freed, it will push out a small block. It will push it out of the cache. So and the bin can contain only up to 6 blocks. So if we free 6 maximum sized blocks for a particular bin, they will push out all smaller blocks out of the cache. And now the cache will contain only these 6 blocks. Then, if we allocate these 6 blocks again, they'll come out of the cache and they'll leave the cache empty. And once the cache is empty, we can do more allocations, and the allocations will come from the system allocator, guaranteed. This is what I call the plunger technique for bypassing the OLE-AUT32 cache. So we're going to start with an empty cache, and first we're going to allocate 6 maximum size blocks from each bin, and they're shown in blue on the slide over there. So we've allocated them. The next step is we're going to allocate some blocks of whatever sizes we need for our exploit. There they are, the green blocks. Since the cache was empty, the green blocks came from the system allocator. Then we're going to free some of the green blocks, and they will go into the cache. And this is what we want to avoid, because having them in the cache will prevent other pieces, other components of IE, such as ActiveX controls, from getting these particular blocks, because ActiveX objects don't use the same allocator. They use the system allocator, but not the OLE allocator. So to push these blocks out, we're going to use the 6 maximum size blocks, the blue ones. We're going to use them as a plunger, going through a tube. And by freeing the 6 maximum size blocks, we're going to push out the smaller green ones. And then we can allocate the 6 maximum size blocks again, and we're going to leave the cache empty. And we're going to have our blocks freed through the system allocator. So we get everything that we want. And by using this technique, we can completely ignore the caching scheme that's implemented on top of the system allocator. So I have implemented this technique in this library called heaplib, and it exposes a number of different functions for manipulating the heap. The 2 most important ones are alloc and free. They implement the plunger technique, so you don't have to worry about any of this. You can just call alloc some size, and you'll get a block of that size, and then you can free it. All of the plunger stuff is just handled internally. The library supports Internet Explorer. I've tested it on 5, 6, and 7. I mean, the way IE uses the heap hasn't really changed much between these versions, so the same code just worked. It's an object-oriented API, so you create a class and you have a number of functions that you can call. It has some cool functions for logging all allocations on the heap and also outputting debugging messages. I will show you how this works. You have to have the WinDBG debugger attached to Internet Explorer, and then you can get debugging information about exactly what blocks are being allocated and where. So that's very useful for making sure that your understanding of how the application uses the heap is actually correct. You can also see the result of your actions on the heap. You can see the result of your code. We have the functions, as I already mentioned, we have the functions for allocating and freeing blocks of arbitrary sizes and contents. I mean, this is the most important part of the library. And we also have a couple of functions. They're more high-level functions for heap manipulation. For example, we have functions for freeing the look-aside for blocks of a particular size. We have functions for freeing chunks to the look-aside or to the free list. Unfortunately, the high-level functions don't work on Vista because Vista uses, and also IE7 on XP, because it uses the low fragmentation heap, which doesn't have a look-aside. So those particular functions are specific to the heap implementation. But even on Vista, you can still use your basic building blocks, the alloc and the free function. So once somebody with more free time than me goes and reverses the Vista heap, the low frag heap, and figures out how it needs to be manipulated and tweaked, you can just write a new high-level manipulation function using the lower-level ones, and then you can plug it into this library. So here's some simple code for how to use the library. First, we import our library with the script with a script tag. It is called heaplib.js. It's a very imaginative name. Then we're going to create a new heap object, which is an instance of the heaplib.ie class. And the .ie is there because I was going to implement the same techniques for other browsers too. I haven't gotten around to doing it yet, but if somebody wants to play with it, feel free to send me a patch. Then we're going to call the garbage collection function GC, which calls the garbage collector, and it also flushes the OLE cache of free blocks. So after we've called the GC function, we've ensured that the heap is in a clean state, and we're ready to manipulate it. Then we'll turn on heap debugging, and we will allocate 2 blocks using the heap alloc function. The first argument of that function is either a size or a specific string. If you pass a size, then the library will allocate a block of that size, and it will fill it with just basically A characters. If you pass a specific string, then the function is pretty much equivalent to strdup. So you're going to allocate a block of the same size and fill it with this data. So this is the method we use to put specific blocks of shell codes or vtables or something else on the heap. The second argument to the alloc function is a tag. In this case, we use foo. You can use any number of tags for different allocations. And the tag identifies the specific block that you've allocated there. When you call the free function, you pass it a tag, and the free function will free all the blocks that have been tagged with that particular tag. So you can use this to allocate 3 blocks and then free the one in the middle, because you're just going to give the one in the middle a unique tag, and then you can refer to that particular allocation. And finally, we'll turn off debugging. I will do a little demonstration of how this works. I have a VM here, Windows XP. Here's the JavaScript code for heaplib. Here's this HTML file that uses it, and here's the actual code that will get executed. The code is identical to what I just showed on the slide. But before we run it, I'm going to attach the debugger to Internet Explorer. And the communication between our heap library and the debugger happens through a number of conditional breakpoints, which I've repurposed some of the ATAN and ASYN and ACOS functions in JavaScript. And if you have a special magic value as the first argument, that the conditional breakpoints will output special debugging information. You can read the paper for more details like that. I also have 2 breakpoints on RTL allocate heap and RTL free heap, which will be used to print out the results of all allocations and frees. So I'm going to let Internet Explorer run, and make this smaller. Yeah. I'm going to run the code, and if you look at the debugging output here in WinDBG, you see that we started by flushing the cache, running the garbage collector, flushing the cache again just to be sure, and we enabled heap breakpoints. After we enable the heap breakpoints, we'll see a trace of all allocations that IE does. Here we allocated the first block, which is 512 bytes, and this is the address that we got. This is the address of the block. Then we allocated a 16-byte block. This is the BBBBB allocation. The 16-byte block was allocated at this address. Then, when we called the free function here, it deleted the references to these 2 blocks, and then it flushed the OLE out 32 cache. And during the flushing, the 2 blocks that we had just allocated were freed. So this is how to use the library. Yes?
What's the log for the first allocation? You have 3 allocations.
No, I have 2.
What about this?
Oh, sorry. Let's look at the source. Yeah, that's just a spurious line. In the actual source, I only have 2 allocations. So, sorry about that. You think after I've given this presentation a couple of times, I would have my demo at least working right, but all right. Oh, and by the way, feel free to ask any questions at any time. So you can interrupt me if you want me to elaborate on something. So what can we do with this? Here are a few examples of how to manipulate the heap. Now, this you cannot fit even an introduction to the heap and the heap algorithms in a talk, and much less one part of a talk. But I will give a very brief overview to sort of give you a feel for what kind of level of detail is required to actually use this technique. Here's how the heap works. It's pretty much taken from Matt Conover and Odette's presentation from CanSec a couple of years ago. This is the heap before Vista. It's pretty well understood at this point. The heap allocator manages memory in blocks, and each block can be either free or used. Used blocks are the ones that the application has currently allocated. When an application frees a block, the allocator will try to coalesce that block with the other free blocks around it to reduce fragmentation. So if you have 2 blocks that are right next to each other and you free the first and you free the second one, they'll get merged into one bigger block, and then that will get freed. When you free a block, it goes onto the free list. There are 128 free lists. These are the doubly linked lists of blocks. Each of them is for a specific size. For example, the first free list is for blocks of size 8. The second one is for blocks of size 16, and so on. Free list 0 is special. It contains all blocks that are larger than 1024. I believe they're sorted by their size. In addition to, so if you're allocating some memory, if the application allocates 8 bytes, the heap allocator will go look into the free list for the 8-byte blocks, and it will just get that block, mark it as used, and return it to the application. If the free list is empty, then it will have to get a larger block and split off an 8-byte chunk. In addition to this standard free list management, we have the lookaside, which is very similar to the OLE cache that we discussed previously. The lookaside is a singly linked list for blocks of certain sizes. Again, you have lookasides. You have lists for, the first one is for blocks of size 8, the second one is for blocks of size 16, and so on. The thing about the lookasides is that they go through a much faster code path because there's no merging, there's no coalescing. So when you free an 8-byte block, it will first go into the lookaside list, unless that lookaside list is full. There's a maximum capacity for the list. And adding it to that singly linked list is much, much faster than going through the full doubly linked list free list management. When you allocate an 8-byte block, first the heap allocator will look at the lookaside list, and if there's a block there, it will just return that. And again, that's a very fast operation. You just have to remove it from the linked list, and that's it. If the lookaside is empty, then it will have to go to the free list and perform the full operation. I've already described how the free algorithm works. Blocks that are larger than 512 bytes are not handled by the standard heap allocator. They get allocated directly with virtual. Oh, that's the free algorithm. Blocks larger than 512 get freed directly with virtual free. Blocks smaller than 1K get freed to the lookaside unless the lookaside is full. In that case, we would coalesce the block with the free blocks around it, and then we would add it to the appropriate free list. Oh, sorry. Shit. You should have told me that I was actually driving this without full screen. So the allocate algorithm works pretty much the same way, but in reverse. You know, large blocks larger than 512 get allocated directly from the kernel with virtual alloc. The smaller blocks get allocated from the look aside if it's not empty. If it is empty, then we go and look at the free list. And finally, if we've used up all the memory and there are just no free blocks anywhere, we just get more memory for the heap using virtual alloc. So here are a few examples of how you actually use these techniques to manipulate the heap in specific ways, and all of these are based on things that I've actually had to do to develop various exploits. For example, if one of the problems with heap exploitation is you don't know what the initial state of the heap is. You might have fragmentation on the heap. So remember in the beginning of the talk when I showed the initial heap feng shui demo, we started with an empty heap, and then we allocated 2 blocks, and they were right next to each other. This is what you want. But if the heap contains holes, then allocating 2 blocks, when you allocate 2 blocks, they might actually go into the holes, and they might not be next to each other. So on the slide there, we have 2 holes, and our blocks are going to get there. And we don't want that. We want them to be next to each other. So to deal with that, we're going to defragment the heap, which can be accomplished by allocating a large number of blocks. It's pretty simple. You just do a loop. You allocate blocks of a certain size, and these blocks will fill out all of the holes, and then they'll fill out some more. And finally, the heap layout that we'll have at the end will be pretty much equivalent to a clean heap that doesn't have any allocations in it. Yes?
What if your block is bigger than the block? What if your block is bigger than
Now, usually when you deal with heap exploitation, you have a specific block size that you're interested in. For example, for this particular exploit, I needed 2 blocks that were 2010 in hex, of size 2010. And I needed these 2 blocks to be next to each other. So when I defragment the heap for this particular size, there might still be holes and fragmentation, but there will be smaller than 2010. And I don't care about those holes. I only care about the holes that are large enough to fit a 2010 byte chunk. So after this defragmentation, the next 2 allocations for this size are guaranteed to happen next to each other at the end of the heap. The next technique is for putting a block on the free list, and I think I mentioned this a few slides ago. The problem with the free list is that if you try to free a block, it will get coalesced with the free blocks around it, and when it gets coalesced, you'll have a free block of a different size, and it's pretty much unpredictable size because it depends on what the free blocks around it are. To deal with this, we're going to, if we want to put a block of a specific size on the free list, we're going to allocate 3 blocks, and then we're going to free the one in the middle. When we free it, we'll get a hole, but because the other 2 blocks next to it are allocated and we have not deleted the references to them, that free block in the middle cannot get coalesced. So we can use this to ensure that we have a block of an exact size on the free list. We can also manipulate the look-aside pretty easily. To empty the look-aside, remember that it's a singly linked list. It just has a certain number of blocks. It also has a limited capacity. So if we want to empty the look-aside for a certain size, like 512 bytes, you just need to allocate a bunch of these blocks. So we allocated 100 blocks of this size. The look-aside is empty. The first few blocks will come from the look-aside, depending on how many blocks there are on the list. And then after it's empty, we'll just keep allocating some more from the actual system heap. And then when this loop is done, the look-aside will be guaranteed to be empty. If we have an empty look-aside and we want to put something on it, we just need to empty it first, and then we're going to free a 512 byte block, and it's guaranteed to go on the look-aside because the look-aside is empty. We can use this to free three. I was working on this exploit where the program was allocating, I think, 3 blocks of a certain size, and then the 4th block was the one that I had to control the contents of. It was an uninitialized memory bug. So what I did in that case was I freed the look-aside, and then I emptied the look-aside, and then I freed 4 blocks of that size. And the 4 blocks went on the look-aside, so now we had a linked list of these 4 blocks. Then the application allocated the first 3, and when it got to the 4th one, it was the 4th block that I had just freed. So I had that level of control over what data the application would get. One of the cool things with the look-aside is that you can use it if you're not dealing with an ASLR system. You can use it in a pretty neat way to exploit object pointer overrides without having to do any heap spraying very precisely. Remember that when you have objects, you have an object data structure. It points to the vtable, then the vtable points to the virtual functions. This sequence of pointers is very similar to the linked list that we actually have on the look-aside. So what we can do is we can empty the look-aside. We can build a fake vtable that contains just pointers to our shellcode, and then we can free that. When we free it, the head of the look-aside linked list, I think I have a diagram here. So this is the fake vtable here that we freed to the look-aside. This is the look-aside head. It's just a pointer to the first entry in the look-aside linked list. And the look-aside head is in the default process heap. If you don't have ASLR, it will almost always be at a known location. In Internet Explorer, usually it's 150000. That's the base of the heap, and then you can add a fixed offset from that to get the look-aside pointer. So we can use that as a fake object, and the first 4 bytes of it will point to the free block that we freed, which also serves as a fake vtable. The contents of this block will contain a virtual function pointer. In this case, if we're calling the virtual function at offset 8, that pointer, we're going to point it to a jump ECX trampoline, which we can find in any DLL or executable in our process space. And then if we have this code here, these assembly instructions for the virtual function, the address of the object will be an EAX, the address of the vtable will be an ECX. So when we execute the jump ECX instruction, we'll jump to the beginning of the free block. At the beginning of the free block, we'll have a null pointer because this is the end of the linked list on the look-aside. These 4 null bytes will be executed as shellcode. They're equivalent to sub EAX AL. This instruction is guaranteed not to cause access violation or anything, because EAX points to our fake object, which is actually here, and we know this to be writable memory. Then we'll get to, after the null pointer, we'll get to data that we actually control, and we can put a jump there, and then we can have some shell code. So this method, we can get reliable shellcode execution with a fake object and a fake vtable without having to do any kind of heap spraying. We're basically reusing the lookaside linked list to construct a fake object with a vtable. And I'm going to do a little demo of actually using this to exploit a vulnerability. All right. So this is an exploit for the MS-06-067 bug, which is it's the keyframe vulnerability in one of the ActiveX objects. It's been patched. It was patched last year. But it's a pretty interesting vulnerability because the ActiveX object allocates a block, two blocks of a certain size, and they're initialized to 0. They're actually zeroed out when they're allocated. But then, because of an integer overflow, and these blocks are supposed to contain object pointers. They're basically arrays of object pointers. But they're normally initialized to 0. And the ActiveX object, when you trigger the vulnerability, due to an integer overflow, it will loop through these blocks, trying to call a virtual function on these pointers. The ones that are null, nothing will happen because it handles that case. But because of the integer overflow, the code will actually run off the end of the block that you've allocated into the data that's after that. And it will try to use that data as an object pointer, and it will try to call a virtual function through it. So if we control the object pointer that's there, we can use the technique that I just described to build a fake object and get shellcode execution. So I'm going to run the exploit. I have, just verify, I have my breakpoints set here. So we're going to get debugging output from the exploit. All right. So what happened here is you can see we did a lot of allocations for blocks of size 2010. This was to defragment the heap. After that, we needed to create 2 holes of size 2020. And we did this by allocating 5 blocks and then freeing the ones in the middle to make sure that they're not coalesced. And then you can see that here when we freed these blocks, we actually got these addresses like 930 and 68E0, which are right here. So you can see that they're in the middle of the 5 blocks that we allocated previously. Then we triggered the vulnerability. So all of these allocations actually come from the ActiveX object. So we don't have control over their order or sizes, but because we've set up the heap state in a particular way, we do have control over what memory these allocations will actually return. And the 2000C allocations are the ones that we care about. And we see that the blocks that get returned are the 2 blocks that we just freed above here. And we control the data in these blocks. One other thing to note is that the first 20C bytes of these allocations will be zeroed. But the data after that, between 20C and 2020, will be controlled by us. So when we trigger the integer overflow and the loop goes over the end of the block, it will reach the object pointers there, and we'll get shellcode execution. So, was there a question? No. I'm going to disable the breakpoints. I'm just going to let it continue, and we get this pop-up. And this pop-up is actually a message box call from the shellcode. So we got shellcode execution. So this is what you can accomplish with heaplib. To summarize, it gives you a very convenient API for manipulating the heap. You don't have to deal with any of the really low-level details. You still need to have very good knowledge of how the heap actually works and what the results of your allocations and frees are going to be on the heap. But once you have that, you should be able to apply it to pretty much any heap corruption vulnerability out there, buffer overflows, use after freeze, double freeze, and you should be able to exploit it. And finally, I think I have a minute left. Finally, I'll go over briefly about the potential mitigations for stopping this technique. One of the better ones that I could think of was heap isolation. If Internet Explorer actually used different heaps, different dedicated heaps for the different components, then you would not be able to manipulate the heap of some ActiveX object, because the ActiveX object would use its own heap, not the same as your strings use. This is something that could potentially be done in the next version of the browser. The other mitigation technique is introducing some non-determinism or randomness. So if the heap allocator doesn't always return blocks in the same location, you will not be able to predict very well what the heap layout is going to be. And you can probably do this without sacrificing too much in terms of performance or reliability, although it'll make it a little bit harder to debug. So these are the two methods for breaking this technique. I encourage you to stay for the next talk when the WebSense guys are going to talk about this technique they have for detecting heap corruption vulnerabilities. So I'll be pretty interested in actually seeing that myself. So any questions? Yes?
So what about that NX as a mitigation?
The question was what about NX as a mitigation? Well, obviously, if you have NX, you cannot execute your shell code from the heap. What you can still do, though, is you can use the heap manipulation techniques to override data, and that data doesn't necessarily have to be function pointers or object pointers. It can be some other kind of data that the application uses in some way. You can override some kind of permission setting that is somewhere in memory. So obviously, shellcode is a lot more convenient and easier to do more generically. But application data overrides would certainly be possible, and this would be a very useful technique for that. Yes? Yes, the question was about is there a JavaScript library included in Metasploit? After I presented this at Black Hat Europe, Scape, I think on the next day, he was actually in the audience, and on the next day he took that code and wrapped it in some Ruby and shoved it into Metasploit. So it has been there for a couple of months now. It is not as it is not as easy to use as the standard Metasploit modules because it's JavaScript, so it doesn't integrate very well with the Ruby. But you can certainly use it in a Metasploit module. Yes? The question was, what if the collect garbage function was not exposed? Are you a Microsoft developer? If the collect garbage function was not exposed, we would not be able to directly trigger the garbage collector. However, if the garbage collector relies on certain heuristics, such as the number of objects allocated, we would still be able to trigger it. And remember that the JavaScript objects are allocated on a separate heap, so we can allocate as many of them as we want without changing the state of the default process heap, which is the one we care about. So I don't think that removing the collect garbage function is going to be a major obstacle to using this technique. One thing that could break it is if they implement a generational garbage collection schema, or some more complicated garbage collector that doesn't behave that's not as simple to manipulate as this one. So maybe we'll see that in the future, maybe not. Any other questions? All right? Thank you.